Record. Recording in progress. Great. Okay. I will see. Okay. Why it's not moving? Okay, the objective. This is something that we cover. Okay. Chapter objective to review basic concept of beam bending. We talked about beam bending last time, right? Did we derive the stiffness for the beam? Do you recall how did we derive it? Okay, I will review it. I know. Then we have to apply some examples. Okay. Do you remember this? This is the sign convention, right? Basically, the forces and the displacement should be upward. If this is X and this is Y, so force and deflection. And we have two nodes, and we have what? 2 degrees of freedom per node. So the total degrees of freedom 4, right? 4 degrees of freedom per node. And we said that the matrix will be 4 by 4. Okay, and this is what we want to derive. So how did we do, this is, it says, moment are positive in the counterclockwise. Rotation also in the same direction of the moment. You see, phi and m, phi1 and m1, it is counterclockwise. Okay, at node 2, phi to m2, counterclockwise. I know this is not an equilibrium. You cannot have a beam like this. Here counterclockwise and here counterclockwise, and the force is up. In fact, if you tell me, is this an equilibrium? Not an equilibrium. This is just sign convention. We will see another element which is an equilibrium. This is now an equilibrium. And then we'll compare this one with that one, okay? Okay, so what I want to tell you here that the load is the slope of the shear and the shear is the slope of the moment. Do you know that? Okay. How do we relate the displacement to forces and moment? How do we relate the deflection to forces and moment? We have to have an equation that relates deflection to the moment. Second order, right? Moment equal so second derivative of the derivative times EI. EI times the second derivative of the deflection equal M, moment. What about the shear? EI third derivative. That's it. So if you know the deflection, you can relate it to the moment and to the shear. Now, what about the rotation? Phi, how do you relate it to the deflection? It's just the slope, right? If you know V, you can find dV. How do you know V? How do V is the deflection. How do you know the deflection? Deflection. No. In terms of finite element, your unknown, your independent variable is V, the deflection. How do you do it? Just like there, we said displacement function. This is what? It's the deflection function. The deflection function will be equal to what? N1, Allah ala shape function. N1 times V1 plus N2 times V1 plus N3 times V2 plus N4. And Phi1 is what? dV1 dx. And Phi2 will be dV2 dx. Okay, very good. So this is what we have discussed. See that? See that equation? That the moment equal EI second derivative of the deflection. And this is the governing differential equation for the beam element. What are the steps to derive the stiffness using direct method? Number 1, select element type. Have you seen that before?
Yeah.
Yes. And then that's what we talk about. You start always with the deflection, not function of n, but function of constant. Then you evaluate the constant based on boundary condition that the deflection at node 1 at x equal to 0 equal V1. and the deflection at node 2, which is at x equal to L equal V2. And then we find A1, A2, A3. And then what? Yes. After finding A1, A2, A3 from here, from the condition here, we go and substitute there. And then how to make the deflection function useful? There is a form to make it useful. How do you make it useful? You gather the term that is multiplied by V1 and you call it N1, right? And the terms that is multiplied by P1, you call it N2, right? And that's what you see here. So this is not good form because it's not clear. What is V1? What is V2? Yes, deflection equal the 4 shape function multiplied by the degrees of freedom. So this one is a row and this one here is a column, right? It's row. Look at it, row. N, row, N1, N2, N3, N4. Because at the end, deflection is a scalar, right? Okay. يبدو لي انكم you are saturated with the speech of Professor Shamshad, right? Yeah, I can see that, right? But really, you are lucky that you have Professor Shamshad. Is really, he's so active, energetic, young person. Okay, relative. Okay. When I say young person, compared to me, right? Okay, N1, N2, N3, N4. N1 is this, N2 is this, N3 here, and N4. Okay, very good. So now we know the deflection. What do you think we'll do next? We want to derive the stiffness. Exactly, strain displacement relationship. And from strain, you can find what? Stresses, and relate stresses to the moment. But all of this will not come here. It will come in potential energy. You see, we are deriving here the stiffness, not based on potential. We don't need strain. We don't need stress. What we need here is just this two relationship. I think you said last time, why we don't have to do it. We didn't need it. We didn't need it here, but you need it in the potential. That's why I put it now. Okay. So what you need is this equation 4.111. You see, moment related to the deflection and shear related to the deflection. And then how do you do it? The two figure, remember the two figure we in the beginning, because if one y is in the same direction of v and the moment is opposite to the moment which is from the equilibrium, Bernoulli. So you evaluate all of this, and then you put this in one vector, and you pull out what? You pull out V1, P1, V2, and then you get the stiffness matrix. Okay, this is, you know it from matrix, you know it from structural maybe analysis. Look at this slide. This is the summary of everything. If you don't understand so far what we have talked about, if everything is summarized here. Okay. Is it clear? Okay. Okay, or cancel. ايش؟ يعني خلي كذا. انا ما فاهم، ما فهمت قصدك اصلا. انا المفروض اقول له ساعتين. Hopefully finish before 1 hour it comes back. Okay. Now look here. Do you know this relationship here? V equal N times D. Okay, what is D? D is V1, P1, V2. What is N? Already you know N1, N2, N3. Do you know, have you seen these two relationships, M and V? Yes, right? Have you seen these two graphs? You see, this one is the finite element, and this one is the beam theory and the sign convention for beam theory. Now, what is F1y? Do you think F1y equal to V? Yes. You see, F1y equal to V. What about the moment? M1 equal to minus M. You see from the figure. And now go to the note 2. Note 2, F2y equals minus, because the shear here down, and M2 equal to M. But imagine at node 1 you have to put x equal to 0. You have to evaluate the third derivative, x equal to 0, x equal to 0. That's the formula. And what about the node 2? You have to put x equal to L, x equal to L. And you get this equation, and then that's it. This is using only beam theory or bending theory. But sometimes when you have deep beam, what you are going to have? Shear. And you have to consider shear. It means that the slope of this is contributed by two parts. Phi is due to bending, and the other one, beta, due to shear, which means like gamma. Okay? So everything, you have to repeat the whole thing again when you want. So dv dx, before we say that the rotation equal only dv dx. Beta is 0. But if you want to include the shear, then what? Then you have to put beta, and you have to do everything, and you have to relate beta, which is gamma, to the shear. What is gamma? Can you relate gamma to the shear? I think I have to use the board. Gamma. Do you know what is the shear? Tau equal to G times gamma, right? This is gamma is the beta. This gamma is beta there. Okay? Now, what else? Okay. Shear. How do you calculate the shear? If you have something here and you have a shear force V, and this is an area, it will be called V, which is the shear force divided by effective area, not area, because every shape has effective area. So if you have a circle, if you have a rectangle, or if you have an angle, everything has AS. Because this, you will see it in commercial software. It will tell you what is your effective area. Okay, AS. What is AS? AS equal the area times KS, which depends on the shape. So KS for the circle, different than KS for the square, different than the KS for the angle. So if you take the gross area and you multiply it by KS, it will give you what? Effective area. If you divide the shear force by AS, then you will get the shear. All of this is already in the book, and don't worry, you will have a homework problem where you will work out the details. Okay? I cannot go in every details, really. We want to cover so many things, right? So at the end, we got a stiffness here. Look at the stiffness, including the shear. Now you understand what is KS. Don't tell me what is KS. KS, it depends on the shape. Circle has different. If you go to Google and you say shape factor, it will give you KS for all the shapes. KS for the circle, KS for square, KS for the angle. Okay, so this phi, which is here, is the ratio like of bending to the shear, which is equal to this. Look, effective shear area. If you go to the table, look, effective shear area. Look, effective shear area for different shape, it will give you the effective shear area. Okay, now the question here, when do you use only bending, and when do you include the shear? When do you neglect the shear, and when do you include the shear? Huh? When it is deep, right? When it is deep, okay. So maybe this is good idea in your project, okay? By the way, it's time now to tell me or to write something for me about your project, because already you have a group. You have to meet. You have the group, right? You know, to would work. Everybody got a partner, right? And it's already there. You have to give me 1-page summary of what you want to work on. What kind of software, huh? A4. No, A3. Of course, A4.
Do you have proposals, like a list of proposals for us?
No, just think about it, the thing that will serve you on your thesis or something. Choose a topic which is important. Look at the literature, okay? Just find something. First of all, you have to know one commercial software. See example. There are many examples in the software. Choose one of the examples there in the software. Right? I give you a hint, right? Okay, good. But don't copy. Okay, now let's go to the second presentation. What would be the second presentation? I think it's already here, right? Okay, what do you think is the second presentation? What is your guess? Example? Okay, example. Let's see if you are right. Where is it? Is this part 2? Okay, example. That's the only way. Okay, examples. Yes, examples. Okay, I want you to get to know your names so that if you are away, I can call you by your names. Okay? Zakaria. Just first name. Osama. Zakaria. Osama. Hussein. Amin. Huh? Did you hear him? Tumaini. Tamween.
Yes.
Tamween. Very easy. Tamween. Okay. Huh? Umar. Tamween Umar. Saeed. بهاء محمد رضا محمود مين سعيد very good name سعيد وانت ايش اسمك انت سعيد we have 2 سعيد's okay محمد احمد يوسف حكم محمد ايش عبد المجيد. Can you name them?
Yeah.
زكريا أسامة أيوة حسين أمين إيش تموين أمين Did you understand the first row? زكريا أسامة حسين أمين تموين. Okay, next row. عمر سعيد بهاء عمر سعيد بهاء رضا محمود سعيد محمد أحمد حكم محمد عبد المجيد يوسف. Okay. Everybody here? Yeah. Okay. Now, what do you think? How do we solve this? You already know how to solve finite element. Before even reading this question, what do you think the procedure to solve a problem finite element? What?
Element stiffness matrices.
Element stiffness. So you find K for each element. Then you'll assemble. Then you'll have global forces, global displacement, or unknown. Okay, then the boundary condition. Then you will extract small matrix, solve those, and then go back, substitute, find the forces. This is global. What about if I want to know for each element what are the forces? Then you have to use the elemental stiffness, right? Abd Majid, This is why we call the name. Now I know everybody. زين انت يا يوسف. Okay. Very good. Okay, this is now the beam. It is subjected to two loads. One is vertical force here. Okay, laser pointer and moment. And I think he divides this to how many elements? Two elements, 1, 2. And I think this is X is global and local. Same. There is no transformation here. It's only like that. Because when we go for the frame and inclined, remember, we have to do transformation again, like what we did in the truss. History repeats itself. But you already know it. You know the basic. Very good. Node 1, node 2, node 3. Okay. Can you tell me the global stiffness? It will be what size? The global. It will be what? 3 by 3, 4 by 4, or 6 by 6?
6 by 6.
6 by 6?
Yeah.
Yes. زكريا 6 by 6. ليش؟ لأن 3 nodes and each node 2 degrees of freedom. Okay. Okay. What about element number 1? It will be 4 by 4.
Yeah.
And element number 2, 4 by 4. Then you will assemble it. Okay. Let's read the question. Consider the beam. Let's say the procedure. Assume EI is constant. And then let's remove this one upstairs. A force of this moment. The left end is a fixed support. And the right end. Oh, by the way, how many unknown here? How many degrees of freedom? The one that you will solve. It is 6 by 6, but you will extract what? Are you going to extract what? What are your unknown? 3? 1? Unknown is 1. Abd Majid, unknown. 1. Ya akhi, go to each node and see what is the unknown and add them up. Okay, start with node 1. How many unknown? Nothing. Everything is 0. Deflection is 0. Slope is 0. Go to node 2. How many unknown? 2 unknown. Deflection and slope. Yeah. So V2 and Phi2. This is 2. Okay, go to node 3. Phi3. So it's Phi3 rotation. Because each node, it can have what? Either displacement and rotation. That's the degree of freedom. It's not a truss. This is deflection and rotation. So it would be 3 by 3, right? Okay. Now we can keep going. What is this? This is for element number 1. Phi1, V1, Phi1, V2, Phi2. Okay. What is this? What is this? This is for element number 2. Do you know how to assemble?
Yes.
Okay, assemble. Wow, we got 6 by 6, right? Look, 6 by 6. 1, 2, 3, 4, 5, 6. V1, P1, V2, P2, and V3, P3. Okay, now, this is how many unknowns?
2, 3.
Now you have 12 unknown. Assume that you have 12 unknown. 6 forces and moment and 6 displacement and rotation. Since it is 6 unknown, you need to find 6, right? So that you can solve the 6 equation with 6 unknown. Can you tell me what are the 6 that you know? I think V1 and Phi1, you know it. 0, 0. V2 is unknown, which is at the center. Phi2 is unknown. V3 is known. Phi3 is unknown. Okay, so now you found only 3. 3 unknown here. Okay, what are the other 3 unknown here? F1Y, the reaction at the fixed support. The moment at the fixed support. What about F2Y and F known? F2Y and M2, is it known?
Yes.
Oh, it's given, let me see. Yeah, already. And if you don't have any load, it is 0, 0. Okay, what about the last one? Do you know that? No, reaction. This is unknown because it's reaction. Do you know the moment? 0. Okay, then you can extract 3 by 3. And then you can get, you see, B2, Phi2, Phi3. يا أخي يلا straight forward. صح؟ صح. Then you can solve for this. After you solve for these three unknown, what you will do? You go back here and put them here. It's either 0 and the one that you found, and find the forces. And these forces are the global forces, which means reactions. Finished. What about this problem? Is it 6 by 6?
Yes.
Yeah.
Okay. Now, what are you going to extract? Is it 3 by 3? How many unknown? Here I think you have 2. Displacement, rotation, and here rotation. Is it 3 by 3? But in the beginning, it will be 6 by 6, right? 6 by 6. And from 6 by 6, you extract 3 by 3. Yes. 3 by 3, I'm the matrix. So you solve for this. And you solve for this. Put it back and find the forces. Okay. And then after you find the forces, how did we find the forces? F1y, you multiply this row by this column. You get F1. Okay. How do you show this? Can you tell me how you show this? F1y is minus 1. Because you can draw shear and bending moment from here, right? Okay. What about this one? Can you tell me what is this? This is the shear and force diagram for each element. If you want to draw shear and moment, you cannot draw it from the reaction. You have to do it element by element. So this is now the shear force for node 1. This is the moment at node 1. This is the shear at node 2. And this is the moment at node 2 for element number 1. Okay, what about element number 2? You see, this is for element number 1. Let's check. So how much the shear? How much the shear? If you multiply this row by this column, you get what? The shear minus P. And how much the moment? 0. How much the shear at the other end? P and minus. You see, it's here. The shear is minus P. It is down because P is negative. P is positive upward. And since the moment is negative, clockwise. And do it here. If I give you the forces at each node at the end, would you be able to draw shear and bending moment?
Yeah.
So you'll start with shear. How much the shear? Is it positive or negative? Negative. Straight line, right? And then it goes here. What about the shear here for element number 2? It would be 3P. How come here it is P and here 3P? Because the reaction, right? The reaction, right? Yes, this is the shear. Look, for the same one, you see it's the shear minus P, and then it goes to 3. This is the shear diagram, and this is the bending moment diagram from finite element. Okay, easy. What about this problem? 10 by 10? This is 10 by 10. But you're not going, is it 10 by 10? Why we have 1 and 2 here? We can have 1 here and 2 here, and then 2 here and 3 here. Huh?
We won't be able to account for the load.
No, because if you put node 1 and node 2, what about this force? You see, we put a node here. We have 2 choices: either to use a node or to take this 50 and distribute it to this node and to this node. Then you can use 1 element. But if you don't want to distribute the load, then this is node 1. This is node 2. Node 1 because it is support. Node 2 because it has a load. Node 3 because it is reaction. Node 3 because it has a load. So it will be 5 nodes. 5 nodes times 2, 10 by 10. You want to use symmetry here? Let's do it for the long one and see. If you want to use symmetry, it will be what size?
3 by 3, 6 by 6, 6 by 6. It's much less.
It will be 6 by 6?
Yeah.
Oh, 6 by 6. Okay. Let's do it 10 by 10 first. This is 10 by 10. Look, 10 by 10. We assemble, we did everything. You can use Mathematica, right, to do this. Do you know Mathematica?
Yes.
Okay, right? And then you add them up, and this is 10, and this is 10. Very easy. And then you put, okay, it's 10 by 10. You will extract how many? This is the same question. From 10 by 10, you will extract how many? 5 by 5? 1, 2.
Yeah,
5 by 5. 4 by 4.
I don't know whether it is.
We didn't know. We didn't know. Don't use your mind. Okay. No, why you put symmetry? I mean, I saw 10 by 10. I didn't know about anything. 5 by 5. Yes, 5 by 5. You are right. 5 by 5. And then from this 5 by 5, how come he got only 2 here? What did he do? V2 and what? Oh, most of them zeros, right? And then he got this and substituted back. Okay, and then you go back, substitute, and get the forces. And then you use this for each member. Look, for member number 1, you put this with the stiffness, and you get the forces. You can draw shear and bending moment diagram. Symmetry. Look, symmetry, mashallah. This is the same problem, but you are using symmetry. How do you use symmetry here in this problem? You see, because the mirror image here, 50-50, fixed. So you can use this part. So what are you going to do on this 3? You make it what? You make it hinge? No, how come you make it hinge? No, but it is symmetric. Symmetric means the slope is 0 here. Look, symmetric. So this is what fixed support. Because when the slope is 0 and deflection is 0, it mimic or it is modeled like fixed support. Okay, fixed support. Okay, the size of the matrix, how much we said? 6 by 6. Okay, and your unknown. Out of 6 by 6, you will get what? 2? 2 by 2. Right. What about here? Yalla, spring. Mindfulness. And mindfulness, يعني even if you hate the class, bring your mind. Think about what? Think about your dream in life. Why you want to take master? Why you want to get good grade in this, right? Why you waste your time? You come all the way here, and then you are thinking about what you are going to do after the class. Just bring mindfulness here. Okay? Now, focus with me here. Now, this is a beam with spring. Now, how many degrees of freedom? The degrees of freedom, and go node by node. This is will give you the big size. Okay, it will be what? The size of the big K. 8 by 8. Huh? The deflection at 3 is the same as the deflection of the spring.
As with the displacement of the spring. Use the displacement.
My question is clear. What is the size of the global stiffness? That's it. What is the size of the global stiffness? Huh? 8 by 8?
Yeah.
Again, 8 by 8. 6 by 6? 8 by 8. يعني 8 by 8, 6 by 6, 7 by 7. Okay, the one who said 8 by 8, raise your hand. 8 by 8. Okay, The one who says 6 by 6. Okay. The one who says 7 by 7. There are people who didn't raise their hand at all. You didn't raise your hand. I didn't see it. I didn't see your hand. You have to choose. Okay. I give you multiple choice. 8 by 8, 6 by 6, or 7 by 7. Again, 8 by 8.
8 by 8.
It gives you a chance to revise it. Okay, 8 by 8. Okay, you raise your hand. Okay, you raise your hand. Okay, don't say it like this. I don't know if you are raising your hand or if you are say like that. Okay, 8 by 8. Okay, 7 by 7. 7 by 7. Okay, 6 by 6. Okay, let's see. How many at node 1? How many at node 1? It's part of the beam. It is part of the beam. And we know in the beam, it has 2 degrees of freedom. Huh? Yeah. At node 2, it is part of the beam. 2 degrees of freedom, 2 by 2. So you have 4. At node 3, it is part of spring and it is part of the beam. Which one has more? It is the beam. 2. Node 4, it is spring. And in the spring, there is only 1.
But we'll
But
put
we will
zeros.
expand
But we'll
the
put zeros.
matrix.
Huh?
We will expand the matrix.
Yes. Yes, you have to combine it. 7 by 7. It's going to be 7 by 7.
Other nodes are 2 by 2. So they'll be the matrices will be 4 by 4, right?
Yes.
We'll have to make a 4 by 4 matrix for node 4 as well in order to combine it with the other.
No, you can combine it. 3, 4, 3, 4. That's 2 by 2. Still, you can combine it. 3, 4, 3, 4.
It's convenient. So it's 7 by 7.
Yeah, it's whatever.
8 by 8, there yes, zeros and columns.
So you are saying 8 by 8, the global? The global is 8 by 8?
Yeah.
I'm explaining to you now that it is 7 by 7. And you are still insisting that it is 8 by 8. I mean, it is 0 here. You know that the spring can, this one, how many degrees of freedom in the spring? Only 1. You cannot tell me that it will move here. Because degrees of freedom in spring and trust, only 1. I think you need the solution. Is it 7 by 7?
Yes.
7 by 7. Abdul Majid. 8 by 8 or 6 by 6? Hello. Okay. Look. Okay, 3 and 4. Look, 2 by 2. You see? So 1, 2, 3, 4, 5, 6, 7. Okay. How many degrees of freedom? This is 7 by 7. But how many degrees? Yalla, قولوا لي. Out of this 7 by 7, you would extract what? 1, 2, 3 only? 3 by 3? What is it? Name them. Phi2, then V3, Phi3. That's it? Okay, let's see if this is correct. Yes, it's here. And once you solve for that, then you can find the forces. And once you see the forces, then see, you can find the forces. Now, can you draw shear and bending moment diagram to this? How? You'll make a cut? No, don't make a cut. You have to use element stiffness. But for this one, it's okay. Already, if you use K for this stiffness and you use the degrees of freedom for 1 and 2, it will give you the first 2 terms, it will give you this one and this one. The second 2 terms, it's not here. It will give it to you as if you made a section. It will give you the shear and the moment. Okay? So